All right, I apologize again for running late. So you guys, tell me, how many of you guys are like juniors right now? Seniors? Graduate students? And then sophomores? Yeah, okay, freshmen? Awesome, okay, good. Well, great. So my name is Derek Hansen. I'm a faculty member in the cybersecurity program. I've been here 11 years now. And I'm excited to talk a little bit about some of the fundamentals of cybersecurity, some of the terminology that you guys should know, and then a couple of, I guess, intro level stuff on encryption and how it works, especially in the web. So often we use the term cybersecurity. Before that was really a term. The main term we talked about was information assurance. So the goal of a lot of cybersecurity is to protect different, what we might think of as services that people want to have. So we're going to go through a few of these. So information assurance is to protect and defend information by ensuring and then each of these is kind of a key term that we'll go through. So actually I can't.
It's up.
Anyway, you can move it. So availability, integrity, authentication, confidentiality, and non-repudiation. So these are all kind of specific terms that we use in cybersecurity. How many are familiar with these terms already? Okay. And so we'll kind of go through them and talk about different kinds of attacks and how they might influence things. So first of all, you guys probably know there's you hear about new cyber attacks every day, and the numbers just keep going up and up and up. And there's a lot of job growth in this area, lots of different kinds of attacks on all sorts of devices, including embedded devices. And so, there's kind of a need to understand this. This is a cube that we sometimes refer to as just the information assurance cube or model. And it's kind of useful in just diagnosing a different kind of attack. And so there's 3 dimensions that they show here. So one of them is these 5 security services, and I'll go through these in a second. But for example, confidentiality, you probably know just from the meaning of that word. It's like gaining access to information you shouldn't have access to, right? If you get someone's password, then that's a breach in confidentiality because they want it confidential and you've gotten it. So these are different security services. Then here we have information states. So we can think about was the data compromised while it was being transmitted? So maybe someone listened in on the cables as it was transferred through or through the air waves through wireless, right? And that would be a breach during the transmission information state. Or if it was in storage, meaning long-term storage, or was it breached during processing? So something like a buffer overflow, if you've heard that, would be an example of some kind of processing is happening and there's some problem that emerges. And then we have security countermeasures. So these are things we can do to try to prevent attacks. And so we might think about technology solutions. So you install a firewall on a server that doesn't let certain kinds of traffic in or out. You might have policies. So like the university here has policies about if there's a breach, then they have this kind of checklist that they have to follow. Okay, here's who we need to notify, including the lawyers, and then what do we do to report it or to make sure that it doesn't kind of get worse and spread. Or it could be as simple as policies about passwords. Your password has to be this length and this complexity. And then you've got people, and this is like training people, right? So it turns out most breaches occur because of people that click on a link in a spam email, phishing email. And then that's the entry point for people to then get in. And if you can get in as an administrator, say, or someone who has a lot of access to things, then you can start putting stuff in the system and hiding the tracks and all this. But a lot of times the initial way of getting in is through that. So if we think about, like, we could pick some kind of attack and then sort of consider what security services are relevant, what information states and countermeasures. And it's just a nice, I guess, framework. So let's talk about the different, these different types of security services. So confidentiality, I think, is the easiest one. So the assurance that information is not disclosed to unauthorized persons, processors, or devices. You guys have, who's heard of FERPA or HIPAA, right? Pretty much everyone, if you go to the doctor's office, they're not supposed to have like a list of everyone who's been there for the last week that you can rifle through, right? So this can be even on paper. HIPAA says doctors shouldn't talk to each other about patients in the hallway or in the elevator where other people can overhear them. But then, of course, there's strict laws, like HIPAA requires that if you're storing medical information, it has to be encrypted at rest, meaning it has to be encrypted on the device. Maybe some of you, like, my stuff's encrypted on this machine, so if someone got in and couldn't log in as me, then they could look at all the bits and they would be encrypted. It would be hard to, break that, right? So that not everything is encrypted at rest, but that's confidentiality. All right, integrity. We don't mean the kind of like Sunday school integrity. That's great. You should have that kind of integrity. But your data, if we talk about data having integrity, we mean data can't be created, changed, or deleted without authorization. So it's all about modifying something. So does anyone know, how could you know if something's been modified? Checksum. Yeah, we might have a checksum or a hash is how we do it usually, where you have some kind of, we'll talk about hash algorithms later, but you can sort of run all the bits through some hash algorithm and it spits out, you could think of it almost like a unique ID. And if even one bit changes and then you run it through that same hash algorithm, it spits out something it gives you a totally different answer. So there's ways that we can sort of check, did something get modified or not? A breach in integrity, any 24 fans out there? Jack Bauer, did you guys watch that show? It's been a while. It's been a while, maybe. It's a fun show. But they have a guy come in and he like takes an axe to the servers, or something, right? If someone breaks the machine, that's a breach in integrity, right? That data is like, it's been changed, deleted, whatever, right? So anytime we modify something, that's what we're talking about integrity. Availability. So this is like, is the service available to be used the way it's supposed to be used? So can authorized users actually have access to it? So maybe you've heard of things like a denial of service attack. That's where, or they're pretty much all distributed denial of service attacks. So this would be where some group, say Russia, wants to disrupt things in Ukraine. So in 2014, this happened pretty severely before they invaded Crimea. They had these distributed denial of service attacks and things like they would basically overwhelm servers with so many things trying to request stuff that it became unavailable to people for normal use. And so in that case, they were trying to overwhelm lots of different services, banking services, critical infrastructure services, and then no one could do banking because all these bots were kind of hitting those things. So that's a distributed denial of service attack. There's other kinds of availability attacks, and these are we have sometimes people come from Idaho National Labs, and their job at that national lab is to protect critical infrastructure. So there's like the power grid or water treatment facilities, things like that. And they say, most of you guys, most of the time in cybersecurity, you're dealing with like confidentiality, and you're trying not to get people's stuff stolen, information stolen. He said, what we worry about is availability, because if the power grid goes down, it's not available, you're in big trouble. And then authentication, another security service. This is just where someone should be able to authenticate as themselves and prove that they are who they're supposed to be before gaining access to something. And I won't probably emphasize these quite as much, but non-repudiation. This is the idea that if you're doing like e-commerce and you're buying stuff from other people, you want to have knowledge that you're talking to who you think you're talking to, and that if you bought something, it was actually delivered, like this kind of proof of delivery. And it's kind of beyond the scope of what we'll get into at this point. But the point is, these are security services that we talk about. And sometimes you hear about the CIA triangle, and that's the confidentiality, integrity, availability. Those are like the three, or the triangle, like the most important ones. Questions on any of that stuff? Okay, so I'm going to assume you guys, just from kind of prior knowledge, you know when data is in transmission or in storage or being processed, because you're in major. So, but it can be useful to think about that. And then the countermeasures, I think I already mentioned a little. So let's give you a scenario of like a certain kind of attack. So one very common kind of attack on websites especially, but also other things, is where you try an injection. So the idea is that you try to get someone's server to execute code that wasn't meant to be code. So for example, if I go to a website and it has like a login field, like normally you think, okay, someone's going to put a username in the username field and a password in the password field. But of course, people trying to break into systems are always trying to game the system, and there's nothing that says you can't type in code into the username field, right? And so if in some systems, if you know what's happening on the back end, so for example, let's say you know that they're running PHP, still the most common programming language on the web, right? It's a lot of legacy stuff, but like it's out there, right? So they're running PHP with like a MySQL database that's going to run SQL code. Do you guys know what SQL is? It's like a database language, right, for querying data. If you know that they're doing that, then they might be vulnerable to a SQL injection, which means you put a bunch of code. So basically, you just comment out, what their code is going to, like, if it takes your input and just sticks it into like how PHP runs, then if you put code in, you can have it like comment out the other part that asks for the password, and you can have it do things like return the whole database, or like tell me, there's lots of trouble you can cause. But the idea is injection just means you get your code to execute in some other context, right? So let's imagine that you have a hacker that uses SQL injection to gain access to another person's account. So they say in their code, they say, give me user ID 347's, financial statement or something, right? Let's see if you guys can tell me which of those 5 services, we can go back and look at the queue, but which of those 5 services would have been reached? So we've got availability, integrity, authentication, confidentiality, non-repeat. So someone yell out something.
Confidentiality.
Okay, confidentiality. Are any other ones relevant?
Integrity.
Maybe make a case for that. What would have to happen for integrity?
Well, you're injecting your own code, so it's kind of like the source code being changed. I don't know.
Yeah, it's a little more dynamic because you're not changing the source code, right? Like directly. But if you had it do something other than just view it. So if you said, change the amount of money in the database, then that would be definitely a breach. And you could do that kind of stuff with SQL injection, right? In our exact scenario where they just read it, probably not injection, or integrity, but you could do that. Yeah, so I think authentication, like clearly this person isn't authenticated as that other user.
Yeah, basically.
Yeah, so there's a breach in that one. So those are I think the 2 main ones, right? You could perform with SQL injection other ones, though, right? You could do. There's a famous XKCD comic where it's like this kid runs a SQL injection and he runs something called drop tables, and
They name their kid.
they name their kid, and they call up the mom of the kid and they're like, your son deleted, that means delete all the tables in the database. They're like, your son, deleted all this stuff, and the mom says, oh yeah, good old drop tables, like her son's name was that, like semicolon drop. So the point is that would make it unavailable, right? So that would be a breach of availability and integrity because you deleted and authentication. So each kind of attack could be used to do different things. Now, which of these is most relevant? Was there a breach during transmission, or did transmission work as it should? Yeah, I mean, it passed data along and it's supposed to. So how about storage? In our just reading scenario, I mean, nothing was tampered with really on the hard drive.
Just query.
Yeah, just queried. I mean, it was accessed, but it worked how it was supposed to. And I would argue probably processing is most relevant here because you got someone to like process your code that shouldn't have been processed. And then security countermeasures, we could think about how would we protect against that? We could say, well, we could, I don't know, you guys give me ideas. What might be, any ideas on what you could do to help?
You limit queries to a certain amount of returns. So like if it's like returning a lot to raise a flag or something.
Yeah, but then they could still spy on that one guy's stuff, right? So we could, how about we don't trust the input that they're giving us?
You limit the number of characters you can even put in as username.
So you could limit the kinds of characters.
SQL can use pretty short commands, I guess.
It can. So those ones wouldn't necessarily protect against all of them, right? So I mean, there's a whole technical discussion we won't get into, but you can use something called prepared statements, where essentially you write the query ahead of time, and then any data they give us, we just put in as data. So we don't try to like just take their code and mix it with our code. We just say anything from a user gets inserted as like only textual data, right? So that's one way. Or we could strip away all the characters like semicolons and all that. I mean, there's various ways, but so those would be, they might be technology solutions. We might have policies in place that say all of our code has to be reviewed for SQL injection. This is good coding practice, right? Like we should always check it. We might have people where we train, in this case, it would be training our developers to develop and serve. So that's kind of a high level overview of some of those concepts. And then I want to get into, for a minute, I've got till about 3:10 or so.
Yeah, I mean, we can go
I
longer.
came late, I feel bad. Let me tell you.
But we have the room till 3:30.
Okay, a couple more. Okay, so let me then talk about for a second the attack model, because these are terms that are useful. And then I want to jump over and talk about encryption. So these are just some terms you'll hear all the time in cybersecurity, and they're not always the intuitive meaning that you think of. So a threat, if we say there's a threat that, I mean, we might talk about this in even non-cybersecurity terms, there's a threat that Russia could drop a nuclear bomb, right? That means it hasn't happened, but it's something usually bad, right? That could happen. Right? It's like, we could say it's a viable threat because they actually have nuclear weapons or something, right? But maybe unlikely threat because, mutually assured destruction, right? So when we talk about threats in cybersecurity, we could say, well, there could be a threat that our data will get compromised, or a threat that the power grid will get taken down. We could talk about how risky, how much risk is there involved in these threats. And so, but anyway, that's a threat. So vulnerability, we could talk about, if there's something that's vulnerable, we usually mean, or even we say a vulnerability, we could say there's a SQL injection vulnerability. That would mean that someone could compromise the system doing SQL injection, but it doesn't mean that's happened, right? It just means you're vulnerable to that. Does that make sense? So, or we're vulnerable to a nuclear attack because we can't really stop it in some cases. Then risk, we think of as a combination of two things. A lot of cybersecurity is assessing risks. There's no way to get rid of the possibility of bad things happening. There's no way that you can protect against every kind of attack, especially if you have what we call advanced persistent threats, APTs, like you have a nation state, China or someone that if they're determined to get into your system, they'll do it right away. So all you can do is try to minimize risk. And it's a really cost benefit kind of analysis. And so when we think of risk, we think about the probability of some event happening. So it's really unlikely that a nuclear bomb would attack, but the consequences are huge. We multiply those, right? Probability times consequences gives us a pretty good idea of how seriously we should consider that. So we invest a lot of money into trying not to get attacked by a nuclear bomb because the consequence is so huge, right? So with cyber attacks, it's similar, right? We can think about, well, some things could happen, but their consequences are a big deal. All they can gain access to is stuff that's not really that confidential. So we don't, it's not as big a deal. But you always want to consider those two things. And then an attack means when someone is attacking someone, they're actually performing some attack on some vulnerability, right? So they're in the act of trying to type in the SQL injection, right? Or there has been an attack, means they actually tried to do that. And then an exploit means a successful attack. So they exploited the SQL injection, then that means they successfully performed that and got some data or something. Those are just terms that show up. Okay. Questions on any of this? All right, so let's talk about encryption and how it plays into cybersecurity. So some of this, yeah, it'll be a little review, but encryption is the science of communicating with secret codes, right? And it's super important to our just economy and world today. You can't buy something online without encryption, right? You can't communicate securely without encryption, right? People will listen in on it. And it deals with all of these. Which one's missing here? The 5. Anyone? Yeah, availability. So I mean, like indirectly, maybe it affects stuff, but it doesn't really affect availability. So you could have a perfectly encrypted system and someone could have a DDoS attack, one of these things where they get a bunch of bots to overwhelm your server. It's like encryption's not relevant. Sorry, guys. There's other ways we try to protect against that, but it deals with all the rest of these, really. So here we have encryption. We have a plain text message, meaning it's not encrypted. We run it through an encryption algorithm, and then we get just a bunch of ciphertext, which is going to be, for all intents and purposes, unreadable, right? And then we can decrypt it using some kind of tool that turns it back into plain text. So that's probably similar. Now, there's 3 kinds of cryptographic algorithms that are commonly used, and we'll kind of go through each of these. The first one is called secret key or symmetric key cryptography. Secret key because if the key gets compromised, then you're in trouble because the same key is used, and here you can see it's yellow. The same key is used to encrypt and to decrypt. So if someone gets a hold of that key, they could decrypt anything that's been encrypted with it. The nice thing about it is it's pretty fast to use. And so I'll show some examples in a minute of this kind, but and so often we use these in combination, and then public key in cryptography is, in my opinion, one of the greatest inventions of the last century. It underlies so much of what we do, but we don't even know that it's happening. But the idea, and it's a little more complicated, we'll talk about it in a minute in more depth, but the idea is you have 2 keys that come in a pair. So they're 2 mathematical numbers. They come in a pair, and one of them encrypts and one of them decrypts. And you can't decrypt with the one that you encrypt with. And that simple little mathematical puzzle lets us do all sorts of cool stuff. Like, how would you send a secret key? If I want to sell something to someone on the other side of the world, how would I get a secret key to that person so that we could say, let's use a secret key? There's no secure way to do it, really, right? It's not It's not obvious. Like, do you call them up? Well, what if someone listens in on that? Do you send them, no, it can't say, can you send them any electron? No, none of those work. But if we use public key encryption, we can do stuff like that, and we'll explain how. So you couldn't have like secure communication without public key, but we usually use them in combination. Then the last one is plain text, and this is also, is hash functions, where we take plain text, convert it into ciphertext, but notice there's no way back. So when you hash something, you're turning it into some gibberish, but you can't ever get from that gibberish back to the original. At least you're not supposed to. Okay, so let's talk about symmetric key encryption. So maybe some of you have heard about like AES, which is a form of encryption, or DES is kind of outdated. So, and what happens is people come up with a new algorithm, and then like people figure out some way to sort of, where it's not as good as they thought it was, and so then they update it. Usually if you add a bunch more bits, then it becomes really secure. That's what, like AES, if you have enough bits on it, then it's okay to use. If you don't, then it's not. But in any event, it's really nice because it's fast, and you can encrypt and decrypt computationally pretty cheap. So when we use, like you've gone to websites that have HTTPS, and it's that means it's secure, they're gonna use a combination of asymmetric and symmetric. Initially, they'll use asymmetric to kind of pass around a symmetric key, the same key that gets used to encrypt and decrypt. But then all of your communication at that point will all just be done through symmetric key encryption because it's so fast. Bog down your computer. Public key encryption is a little more complicated, and we there's a math class on encryption that you could take here. It's like, I don't know if I know the number. Anyone know? Math, it's a 400 level class, but you guys would have taken the prereqs and stuff for it. But if you're interested in it, they go pretty deep. But the idea is that you have a pair of keys, and one of them encrypts and one decrypts. And what you do is you arbitrarily just pick one of those and you say, this one's my secret key. And then you give the other one to the whole world and say, that's my public key. And so we sometimes call it secret key cryptography, or public key cryptography. And so it's based on, I'm not going to get into the details of this, but it's based on this kind of these one-way functions where if you imagine the problem 9 times 16, it's really easy to calculate that. We could do that, with our calculators pretty easily. But if I said factor 144 into specifically, 9 and 16, then there's that's a lot harder problem. And so they call this a one-way function because one direction, it's really easy, and the other direction is hard. And then what we end up doing in some forms of encryption is you create a key, which is like big prime numbers. And if you know that key, you know what that prime number is, then it's easy. Just like this is easy, right? The one-way function makes it simple to perform. But if you don't know that key, you'd have to try out every combination, like every factor of 144, but a much bigger number. And again, this is a simplified idea. But if you know that, then you can kind of get to the answer. So that's the idea. And RSA is an example of one. Technically, it's been broken, but if you add enough bits, then it still works. And people develop new algorithms. So one thing that's interesting to note here is that, when you were a kid and you pass secret notes to people, you had some algorithm let's map the letters to numbers, or let's move forward 5 spots in the alphabet, and write D instead of A or whatever. In that case, the algorithm had to be secret for it to work, right? If someone knew that you mapped number 1 to A and number 2 to B or whatever, then they could decrypt anything, right? This kind of encryption works very differently, both symmetric and asymmetric. We say to the whole world, we say, we're using RSA, 2040-bit encoded stuff. So everyone knows the algorithm. What they don't know is the key. So when your browser talks to like a server, it says, do you know how to speak, this algorithm? Like, can you, like, we're going to use this algorithm. Is that okay? And it says, yeah, that's great. So like everything's known, which algorithms, but you don't know the key. Okay. So those are what we have to protect. So let's, so really this, well, we'll talk about how this works with the key diagrams, because I think it's important to see. So let's say we want to send a secret message. We always, in cryptography, you always talk about Alice and Bob. So Alice's name starts with A. Bob starts with B. If you need other characters, you add other, people with letter C. So Alice here has a message. And if she wants to send a secret message to Bob, remember there's these two keys. And we're going to assume Bob may, and actually, these should be different colors. Anyway, Bob has two keys. He gave everyone in the world his public key. He kept his private key. And remember, anything encrypted with one can be decrypted with the other. And by the way, that can work in both directions. We'll see that in a minute. But so all Alice has to do is say, okay, I'm going to use Bob's public key, encrypt my message, and then I can send this to Bob or anyone else in the world, but the only person who's going to be able to read it is Bob, because he's the only one with his secret key. So the point is he has to keep his key private. If someone gets that, then they can decrypt it too. But as long as he keeps that key private, you just encrypt something with someone's public key and send it to him. What if he wanted to send something back to Alice? What would he have to do? Yeah.
Alice would have to give a public key to everyone, and he would have to use that.
Yeah. So he can't, what if he encrypts it with his private key and sends it to Alice? Anyone could decrypt it, right? But they might learn something interesting. What would they learn? This could actually be useful. We'll talk about it in a second. What would they learn from that? So anyone gets the message and he says like, hi everyone, hi, hello world, right? But they know something, yeah.
They know it came from Bob.
They know it came from Bob, right? So this is a key part of what we call digital signatures, right? So that's super useful. So we can use asymmetric encryption for both of those. So this is a picture of that. So here we have a sender, say Bob. He signs it. In other words, the way that we do this, we combine a couple of things. So we encrypt the message with Bob's private key. We also might as well just send it unencrypted because he already gave everyone, like they can just unencrypt it anyway. So we'll just send the message. And then we can also take a hash of the message because we want to make sure that no one tampered with that message. And so we can hash that message and get this unique identifier for it. And we can actually, I think I have a better picture in a second, but we can then, we can actually encrypt that hash as well. But then the point is here, someone can decrypt it and verify that like, oh yeah, that must have been from here. So that's the core idea. So then hash functions, they're one-way encryption. You don't have a key. And also the hash algorithm is known. What's not known in this case is the input. So most of these will spit out some thing that's a certain length. So like it'll spit out some certain number of bits, and every hash is that long. So you could feed it one letter. You encrypt the letter or hash the letter A, and it would give you, however many bits, this long string of bits, right? If you gave it the Bible, it would give you that many, you hash the text of the Bible, that many bits. You hash a movie, that many bits. So obviously you can't get back to the original from it, right? There's no way to store. The information theory says you can't store, the Bible in that many bits. Right? So, but it's super useful for knowing if something's been tampered with. Right? So if someone's modified something, even one character, these hash algorithms are set up so you get a totally different result. So you can't like hone in on it by guessing. You can have conflicts. So a hash conflict would be where someone, you hash two different things and you get the same hash. That's obviously possible because it's a small sized hash, right? But they're designed that's hard to do with these, and you'd have to, you know, it would take a long time to do usually. So it's, but that's the idea of a hash. And so the problem you can have is, you know, this kind of a hash conflict, but they're pretty rare. When you guys store, here's like a practical application of hashes. Let's say you're collecting username and password information. So do you store the passwords in your database? Never. You should never store a straight password. First of all, the database administrator can see it, right? And you know, we can't trust everyone. But more importantly, like if someone gets access to that database, they just have all the passwords. So instead, what you do is you hash a password, and then it's just a string. And then when someone submits a password into your system, you run it through the same hash algorithm, and you just say, do they match? Because the algorithm's not secret, right? How would you try to, let's say you're a hacker, how might you try to like cause problems with or figure out what people's passwords are? Yeah.
If a password is hashed, it still basically would translate out to the same thing if you know the algorithm. And so often most programs, they'll just do the basic stuff like test for password and 1, 2, 3, 4. And because people do really dumb and stupid password stuff.
Yeah.
So you make an algorithm to go through most likely things.
Exactly. So there's password cracking tools, and it's basically they do, you know, they might call it dictionary lookup or whatever. Like they'll take the most common passwords, and they'll just, you know, feed them through, right? And then chances are someone used admin for their password. Yeah.
Also, if you know the hashing algorithm and you know the hash, if you somehow manage to get a hold of the hashes themselves, you don't necessarily need to know if it's just checking the hashes, you don't need to know the original password.
Maybe you can feed it a hash somehow, right?
You can feed it a hash or find just something that hashes to that value.
Yeah, that's right. So there's other ways too. The other issue here is, well, one thing that we recommend, sometimes you'll hear people talk about salting a hash or salting a password when you hash it. The idea there is that you take the person's password and then you add some random number to it just at the end, like, you know, password 1, 2, 3, and you add a bunch of just random characters and you hash that. You got to remember what those random characters are, right? But maybe you store them somewhere else. It's not like in the database or something, right? So if someone compromised the database, they would have all these hashes, but like it wouldn't actually, if you did a dictionary lookup, if you didn't add all the same, you know, random characters, then you're not going to get to the right answer. So that's a recommended procedure, is to salt your hashes.
So speaking of passwords, as a cybersecurity professor, like, do you use like a password manager?
Yeah, so I would say the two most important things are dual authentication, as much as we all hate it sometimes. That's probably the most important thing you could do, right? And then using a password manager. So have you guys ever been to, like, there's a website here you should all go to and look yourself up. Yeah. So you can type in, and also if you do like a Google security checkup, they do something similar. They use this. So I can put in like an email address here, and this will tell you like all these services that were breached. All these companies that I've been a part of, right? And there's some that I'm sure you've been a part of too. And maybe you had an account when it was breached, maybe not, right? I mean, you know, this was like, if you were using LinkedIn in 2016 or whatever, right? Then they had something. So the point is, chances are, and And some of these will tell you like if it was, so look, this is really sad. Some of these are like just the passwords. Some of them have been hashed. I think, yeah, so they'll tell you like, you know, it was assaulted SHA-1 hash. So that makes you feel slightly better, but you know, did someone get a hold of this? So the point is, you know, I've changed my passwords since those. The other way people get passwords is just through is through the spam phishing emails, right? Phishing emails, because they're like, you can create a website that looks like someone else's website really easy because you just, you know, clone the site essentially. So then you get you get them to click on something and they think they're logging into BYU or Facebook or whatever, because it looks like Facebook login. But then when you do that, they actually just send your password to their own servers. Because if you look at the URL, it's not actually Facebook, it's facebook.xyz.com or whatever, right? Yeah, do you guys know how URLs work? I mean, maybe this is like super practical stuff, but like the last part of a URL, so say byu.edu or google.com, right? That's the domain. That's the part that's verified, unique. When you say they sort of, when you talk to someone using HTTPS, that's what you're verifying, like they are who they say they are. They're actually Google, okay? So they can verify domain. Then there's subdomains, like someone does www.google.com. A subdomain, a www. Whoever owns google.com, they can add anything they want as a subdomain. They could do www. They could say video.google.com or whatever, right? So this shows up all the time on websites that you go to. But people who don't realize this, they see Facebook as a subdomain to some other site, like, you know, xyz.org or something, right? Or some like hacker site. But if the name of it's facebook.xyz.org, then whoever owns xyz.org they could add Facebook, Google, whatever they want on that first part. And you're sending stuff to them, not to Facebook, not to Google. So I always look at, before you click on something, I always just mouse over it and it'll show, unless you're on a Mac, unless you're on Safari, but it'll show like on Chrome where that URL is going to be. Nowadays on your phone, like sometimes you'll see things and they make super long URLs, like the subdomain is like Facebook, you know, something. So then, or like facebook.com, .xyz.com, right? So people don't notice that and click on it and then, you know, enter their credentials and some type of. All right, so let's do the whole signing a document, which can be important. So if you want to prove that you are someone, and here's how we do it. We take our original document, we do our hash function, right, which gets our kind of hash value, our unique identifier, so to speak, of this document. So if someone tampers it later, I can see that it's a different one. I can compare them and know it's been tampered with. So I get that hash value. Then I can encrypt usually the original document and this hash value. So I've got this dotted line around it, meaning I've encrypted it with my private key so that everyone who decrypts it knows I'm the one who signed it, right? Because I'm the only one with my private key. So then if I want to verify it, so I'm like, was that really Derek that sent that? And has it been modified? Then I take, you know, Derek's public key, decrypt it, and I take the original document that was part of it, I hash it with the same algorithm that they told me to hash it with, and I compare the hash with the one that they sent me. And if they match, it hasn't been modified. So I know who sent it and it hasn't been modified. It's cool stuff. I mean, this is like, you know, there's a lot of cool math that's hidden behind this, but like the mechanism's really creative. And this is just different, same thing in different languages. So then the last part then, has anyone figured out one of the challenges with what assumptions have we made here for this to work?
I guess No one else has the private.
Yeah,
You know,
no one else has a private key. Or what if someone says, I'm Derek, and sends a message that's not from me, and they say, here's my public key. So someone could pose as someone else, right? And just say that they're Derek, but they're using their own private key, and all the encryption works fine. And so you're like, oh yeah, it matches. But so really, we have to have some way to manage identity, right? So we have to know, like, well, how do I know that Bob is the one? When he says that's his private key, how do I know it's him? So I don't want to take too much time, but like the idea here is that there are organizations that do this. And so a very common one that's important is HTTPS or SSL or TLS. There's all these names they throw at us, but they're all the same thing. So if you see up in your bar, instead of HTTP and then a website, you see HTTPS and then the website, or it has a lock symbol on Google, then that means that it means a couple things. One is it means it's using encryption. So there's this kind of handshake it does to set up that encryption. Phil could tell you all about it in his networking class probably, but it's, so they set it up with asymmetric encryption and then pass a secret key, like I mentioned earlier, and then you communicate. But they also say the person you're talking to at google.com is actually Google. And the way they do that through identity management is that they issue the keys. So they actually give you, like, here's the private and public key. And you have to prove, like, when you set this up, and it's not hard, there's tutorials online, you just set it up. But like you follow instructions and you have to prove that you own the server. So you put something on the server that only someone with access to the server would have. And then that shows Google that you have access to the server, and that's how it knows that you're Google. And then, so that's the idea. Yeah.
So like, say we're just on a GitHub project, and we decide we want to set up like an RSA key to one of the lab machines upstairs, right? We find the RSA key and put it on GitHub. Is that why we never have to log in? When we're using Site Computer, does that computer feed in our RSA keys to GitHub?
So you can set it up through that I'm not sure exactly the nuances of what you're saying, but yeah, you can set that up in GitHub so that you're communicating across an encrypted channel. And
We do a lot of
SSH.
passwordless authentication with SSHing to different computers
Yeah.
or to GitHub using public keys.
SSH keys, not.
Well, and there's
No,
other.
they're the same. We use it for SSH, but it's an RSA public key.
Yeah, and there are other ways of doing this. So like Kerberos is something that maybe your printer uses to communicate with devices. And it's a different identity kind of thing where it's actually distributing private keys, not public key encryption. And you have to have access to the printer and the device that wants to communicate with it, right? So if you're using Kerberos. So the point is there's different, or PGP is this like, our email's not encrypted typically. I mean, it might be like Google might encrypt it while, if you're using Gmail or something, it passes around. But in general, email is not encrypted, so never send anything you care about through email. Unless you're using something like PGP or PGP encryption, but you're not because everyone else you're emailing would have to be using it. And so it never really took off. There are things that are encrypted, like if you're using, like some of the chat, WeChat or Telegram or whatever, Apple, then those are end-to-end encrypted is what we call that, where there's encryption going from one device all the way to the other. So the company that transmits the data theoretically can't know what you're saying or sending, right? So that's ideally you want end-to-end encryption. And yes, there's ways sometimes we can break that too, but in general, that's useful. The email is not end-to-end encrypted, so be careful what you email. But the point is you have to have some way of distributing the keys, to do that. And there's companies that do that for HTTPS. So that's pretty much what I was hoping to get through, I think.
Great, let's give Professor Hansen a round of applause.
have any posted activities here. I mean, could you, I mean, if you thought about it, maybe give a list of like 3 or 4 things the students could do to, you know, like really simple little things to do, like maybe hashes, a public hash programs.
Yeah, so.
Yeah, I can send it to students, but if you can think of a few things.
So you could go to, so sometimes you have to pay money to turn on like HTTPS because you've got to like pay a company to do some of that validation stuff. There's a service called Let's Encrypt, which lets you do it for free. And so you could like try to set up HTTPS on a server if you know, like install a Apache or something else and set up HTTPS using Let's Encrypt, and that would kind of walk you through the process and give you some hands-on experience there.
Are there like some simple websites that demonstrate hashing?
You could,
like password security. I mean, there's no
Yeah.
simple things that you know that like kind of just help people.
on Ubuntu, you can output your password hash if you want.
You can do, so in Linux, you can run hashes on things and like, that would be kind of fun.
Yes.
Yeah, you could just run, I mean, just Google it. I don't know exactly that, but like, yeah, you could hash a document, you know, and change a character and hash it again. And notice that the hash is totally different, right? You were saying something else? Was that-
So you can probably look up your password hash is on Ubuntu. You can probably just copy that to the terminal and see what your password hash that's stored on Ubuntu is.
Yeah, that's true. Yeah, you could look at where that's stored. There's got to be somewhere.
So I was at the Discovery Museum in San Jose, and they had an exhibit there where you typed in a password, and they had, I don't know, they had like a supercomputer or a cluster that would try to
Try
demonstrate.
to crack it. Right
Try to
there,
crack
yeah.
it. It was very surprising how easy simple terms were. So
Yeah.
maybe you could experiment with your password, you know, your password secure. There's probably a website.
There
that tells you
are
how
a
to-
ton, like, yeah, and most people will say use a password tool that just creates them for you and it manages it, right? Or use a passphrase. Really, the length of your password is more useful than
characters.
the characters, just because it makes it so. I mean, you've got this kind of combinatorial, right? Kind of stuff going on, so you add more characters and there's way more possible. So if you do a phrase, I mean, that's what I do for mine usually. It's like a sentence that's easy for me to remember, but would be really, it's a weird sentence. Or I can like update it by changing certain characters if I want, or use a password. Other things, I mean, there's a fun, actually, I think I have a link to it.
So you can send me a link to a couple of.
I can send a few things,
Send some
yeah.
links to me, and then I'll post it on the boot camp. The activities will be kind of simple and fun, just to try to get you to think a little bit about the security thing. And if anybody has, some ideas and some fun little security.
I know that,
exercises, then I'll post those as well.
Someone found out that you can use accents on certain learning suite text boxes to overload the buffer and accidentally good. I don't know if it's still vulnerable.
Learning Suite used to post the code. The code was embedded in the HTML when it first went out. Oh, it was so bad.
We send in things too, saying
Yeah.
fix this.
So we had when what's his name came to present, he talked about Carlos. He talked about a fun activity he did in his class
Yeah, that's true.
where he'd take like a text document and then you run the hash utility on your program to get a hash. And then the activity was to try and create a hash collision. So change the document in some way such that a hash is the same way. Now it's impossible, basically. You won't succeed. But he says if you just ignore 80% of the hash and just focus on the last like 5 or 6 digits or something. So really you're just looking at a million instead of like 1,000 bits or something.
Yeah.
And then what his class did is he basically said, here's places in the document where you could put in a comma, a fake comma, or punctuation. And so each of those is a bit, right? It can be there or not. So if you pick 10 spots or 20 spots, you can come up with 1,000 or 1,000,000 different little documents you could make that all look the same kind of thing.
So
So
programmatically, you kind of
try and find a hash collision by only kind of trying to collide some of the bits, and it sounded like a pretty cool activity when he talked about it, so.
This is a really fun site that teaches you about some different kinds of web attacks. So like SQL injection or buffer overflow, we talked about today a little, but there's a bunch of other ones. So, and they're presented in a really fun kind of way to understand the concepts. That might be worth going through the hacks.
SQL injection's fun. I mean, you could, if
Yeah.
you want to learn a bit more about databases, you could make your own little database and kill the database with a SQL injection
do that
attack
in our
pretty quickly
In
after.
our 210 class, we sort
Okay.
of set it up the wrong way and then show that like, oh yeah, you can execute code and then we fix it. Okay, so, yeah.
Oh, thanks. Thank you very
All
much.
right.
Again, thanks again, Professor Henry.